Good evening and welcome to these public lectures in celebration of Stephen Hawking's birthday. I'm Anne Davis. I'm here to guide you through the event. We are very pleased to have distinguished speakers with us, Professor Sir Roger Penrose and Professor Eiichiro Komatsu, who are going to offer us some insights about the Big Bang and black holes. But they'll be formally introduced later. This event is being organised by the Stephen Hawking Centre for Theoretical Cosmology, which is part of the Department of Applied Mathematics and Theoretical Physics. The centre is known as CTC for short. Stephen founded CTC in 2007 thanks to a generous benefaction from the Avery Sue Foundation. His goal was to develop theories of the universe which are both mathematically consistent and observationally testable. We're organising this event together with our cosmology colleagues in Munich as part of the strategic partnership between Cambridge and the Ludwig Maximilian University, or LMU for short. This public event marks the end of a week of scientific workshops, which has involved collaboration meetings between Cambridge and Munich. In organising this live stream event, I'd like to express our gratitude to Intel Corporation and their Intel Studios team, and also the media team of Four Wings Creative. Thank you to both teams for making this event possible. It's been a huge effort during the present lockdown, but Stephen Hawking's motto was never give up, and Stephen never did give up. So we're doing our best, and please be patient if we face any technical challenges. We're also running these lectures in collaboration with the Stephen Hawking Foundation. Among their aims is supporting research and outreach in cosmology and fundamental physics at both university level and at schools. So we especially welcome the younger members of the audience this evening. You are our future scientists. Welcome. We hope you enjoy these talks. Now, there will be an opportunity after the talks to quiz the speakers. So we have a website allowing you watching live to ask questions or vote for other people's questions. If you want to ask a question, then please follow the web link on the screen now, using a browser on your phone or laptop, iPad, and follow the online instructions. So to ask questions, please visit www.sli.do and search for Cosmo with a capital C, Q for question. So let's begin our public lecture. One of my Munich colleagues is standing by. It's Dr. Stella Seitz from LMU Observatory, and she will introduce our first speaker and the Q&A question immediately following our first speaker. So over to you, Stella.
Thank you, Anne. It's a pleasure and honor to introduce Professor Eiichiro Komatsu to you. Professor Komatsu is a director at the Max-Planck Institute for Astrophysics in Garching near Munich and honorary professor at the Ludwig Maximilian University in Munich. Professor Komatsu was born in Takaharuzuka near Kobe in Japan. Already as a child, he was fascinated by the night sky, and he was trying to understand how our universe became like what it is today. So he studied physics at Tohoku University in Sendai and obtained his Master of Science degree in 1999. And just 2 years later, in 2001, he received his PhD from Tohoku University. His supervisors were Professor Toshifumi Futamasi from Tohoku University and Professor David Spergel from Princeton University. During the years of his PhD work, Professor Komatsu was already a visiting member at Princeton University and at the Institute for Advanced Study under the supervision of Professor David Spergel. After his PhD, Eiichiro continued working in Princeton and became a WMAP postdoctoral fellow in Princeton University. Then, in September 2003, again, only 3 years after his PhD, 2 years, Eiichiro was hired as assistant professor at the University of Texas in Austin. He quickly climbed up the career ladder to associate professor in 2008 and to full professor in 2010 in Austin. In 2012, he moved to Munich to the Max-Planck Institute for Astrophysics, where he is director since. What is so exciting about Professor Komatsu's research? Why does he receive, or his work receive so much attention? Understanding, measuring, and interpreting the cosmic microwave background of our universe is one of the main research focuses of Professor Komatsu. As we will learn from his talk later, the microwave background provides a snapshot of the infancy of our universe. And if we understand the universe at early times and we know the laws of physics that govern its evolution, we can predict how it should look like today, and we can compare with what we actually see on the night sky. Eiichiro led several analyses of the microwave background data from the WMAP satellite mission, as he will explain in his talk. This allowed him to measure the key parameters of our universe with unprecedented accuracy. Professor Komatsu received many prizes for his outstanding scientific work. Among these were 2 very prestigious prizes for the WMAP science team as a whole. This was the 2018 Breakthrough Prize in Fundamental Physics and the Gruber Cosmology Prize in 2012. For his individual contributions to cosmology, Professor Komatsu was awarded, among others, with the Koshiro Hayashi Prize of the Astronomical Society of Japan and the American Astronomical Society Berkeley Prize for meritorious work in astronomy. Professor Komatsu is one of the world-leading experts regarding the microwave background and its relation to the present-day large-scale structure of our universe. Eiichiro, in addition, is very eager and very experienced in explaining this topic to students and non-experts. This makes him to an outstanding speaker for our evening talk today. Eiichiro has recorded his today's lecture a little earlier to avoid any difficulties with the live stream, but he is also here with us live and he will be ready to answer questions straight afterwards. So as Anne already said, if there is something that you would like to ask, then please follow the website that you will be shown on the screen. But now, enjoy Eiichiro's talk. The title is, Where Are We From? Clues from the Light of the Fireball Universe. So let's go ahead and watch the video.
Okay, thank you, Stella, for the kind introduction. I'd like to thank the organizers of this event for the invitation. Thank you all for joining us today for this remote lecture. I'm Eiichiro Komatsu. I'm a director at the Max-Planck Institute for Astrophysics in Garching, the suburb of Munich in Germany. Today, I'm very excited to tell you about our recent findings on the question, where we came from. To answer this question, we used the data that we collected for the light of the fireball universe. And we used a space telescope such as what you see on the screen now. Before we begin, let me set the stage for my lecture by showing you the animation from the Cosmic Voyage, that's IMAX theater movie filmed in 1996. Although this is not a scientific computer simulation of the universe, it captures the essence of today's lecture very accurately. So let me begin. Let's say our whole universe was in the hot, dense state. Nearly 14 billion years ago, expansion started, and wait, universe began to cool. Space doubles, temperature halves. Universe was opaque because electrons in the plasma would scatter light of the fireball universe. So light cannot propagate straight line. It cannot propagate freely. until the temperature of the universe drops below 3000 Kelvin, at which moment, like this, universe became transparent because electrons and protons would form a neutral hydrogen that would not scatter the light as much as electrons would do. Now, so first thing you have to know is that the universe was opaque before. They became transparent at some point. But then you find lumps of matter in the universe, which already existed during the fireball universe. These lumps of matter would collide each other because they gravitationally attract each other. They grow bigger and bigger by merging together with the surroundings, and they eventually become galaxies. A galaxy contains lots of stars. Each star, now we know, contains multiple planets. And maybe, if we're lucky, one of these planets or many of these planets will host life, such as ourselves. So this animation will tell you that our ultimate origin was already there in the fireball universe. So there are two questions I want to give answers today. One, okay, universe in the fireball universe was bright, it's full of light. Where did that light go? I'll give you a very good answer for that. Second, you saw lumps of matter already existed in the fireball universe. Where did that come from? Because the origin of these lumps of matter, the initial irregularities, would be our origin. We think we have good answer for what the origin was, but to have the definitive answer for this, we would have to keep investigating, and we are hoping that in, let's say, near future, 15 years from now, well, within 15 years, we'll have very good answer for you. Now, let me then tell you that everything I tell you today has solid theoretical and observational foundations. In other words, I don't make stuff up today. If I don't tell you I'm speculating, you can be assured that what I'm saying is based on solid foundation. So relax, sit back, enjoy hearing the latest findings in the research in cosmology. So if you look up the night sky, you see stars. And that is the sky you see in the visual wavelengths. And you see Milky Way, gorgeous. But now, if you have appropriate machine to take the picture in microwave, let's say 1 millimeter wavelengths, then you see the sky that looks like this. The sky is full of the light from the fireball universe. So to answer the first question, where did the light of the fireball universe go? It didn't go anywhere. It's still with us. It's everywhere. We're immersed in light of the fireball universe today. Light of the fireball universe is pouring down on Earth. This is called the cosmic microwave background. So now these days, of course, you think that the air is full of novel coronavirus, and that's very depressing to thinking that way. But I tell you, if you look at the volume of one sugar cube, that's 1 cubic centimeter, there are 410 photons, particles of light from the fireball universe. So we are literally immersed, we're surrounded by the photons of the fireball universe. So forget coronavirus for the moment, at least for next 30 minutes or so. Think that you are in the middle of, you're surrounded by light of the fireball universe. Now, all of that is super complicated, and then you understand this in the head, but maybe you don't understand by heart. So to fix this problem of communication, I teamed up with a movie director, Mr. Kosaka in Japan, who is well known for his beautiful movie for full dome projection. Namely, this is the movie for the planetarium, okay? And we created probably the world's first full dome movie dedicated to the cosmic microwave background, history and physics and research of that. So, but because this is a full dome movie, which I'm projecting on a screen, you have to imagine, okay, that the middle of this screen, middle of the circle would be your zenith, above your head. Then the bottom would be front, top would be your back, sides are sides. So let's begin.
The cosmic background radiation was predicted as a consequence of the expansion of the universe.
The beginning of the universe was like a dense ball of fire. Everything was immersed in light. It was just like the center of the sun, like a fog where light couldn't travel straight. However, when the universe cooled down due to expansion, the fog cleared and light could travel farther. Shouldn't this light reach the Earth today?
This light gives us the oldest picture of the universe that we can ever see directly.
But the wavelength of this light has been stretched by the expansion of the universe, and it has gone past visible light and turned into microwaves. Microwaves that come from every direction at once. That's the evidence for the expansion of the universe.
That's right. So this makes our life very easy when we try to explain complicated concepts such as this one to the public audience. So I hope you enjoy the movie. And then we have a few more of these. So indeed, the visible light has wavelengths, which you can see. And when universe was hot and dense, whole universe was shining like the surface of the sun. But as universe space expands, wavelengths of the light will be stretched to the microwave today. You can't see it directly, but when you have a proper apparatus, you can see it. So what kind of apparatus can we use? Such as this one. So maybe young folks wouldn't recognize this is TV, okay? And if you don't know what this is, just ask your parents. So here is my friend, Professor Hironya Paris, professor at UCL. She's holding a TV which is not tuned to any broadcast signal. So you have this static noise. And in fact, this TV is the receiver of the radio signals. Radio includes microwaves, and the 1% of this static noise is in fact light of the fireball universe. So you don't have to have anything sophisticated. You just have to get TV out of the closet in your parents' house, and that's all you need. But of course, to do the research out of it, we need something better. 1964, Dr. Penrose and Dr. Wilson, working at Bell Lab in New Jersey, USA, used this gigantic radio antenna to study light from the astronomical body called Cassiopeia A. That's a supernova remnant. And if you go to Deutsches Museum, which is one of the world's largest science and technology museum, third floor, you see this 1 in 25th model of the Penrose and Wilson antenna in Bell Lab. It moves, so you can point this to anywhere in the sky that can be seen from New Jersey. And in the same floor, you can discover the real detector system used by Penrose and Wilson experiment. So this is a real thing, no? For a person like me who investigate cosmic micro background daily basis, this is a very important place. So if you look at the photo to the right, in this metal machine, you see somebody taking a picture. Well, that's obviously me. And so what does this do? Light comes from the left and goes into this home antenna. Then you go to the amplifier so that you can see the signal. Signal will be sent to the recorder, okay? That's fine, but then what's important in this apparatus is that there's a calibrator. Very cold, 5 Kelvin, above absolute zero temperature. So what you do is you get the signal from the sky and you compare that signal to the signal of something you know. So you have the 5 Kelvin signal that you know, you compare sky signal to it, and you measure the temperature of the sky. So day one, that Penrose and Wilson turned on the apparatus, they discovered a problem. This recording time goes from bottom to up, and the intensity of light increases from left to right. And what you see here is a very cold signal, the very left, dip in the middle, that's 5 Kelvin. And everything else is above that, which means sky temperature somehow is brighter than 5 Kelvin. And that's a problem because people already knew at the moment that zenith sky temperature, top of our head, at this 7 centimeter wavelength is 2.3 Kelvin. Then you also account for all the things that you know about source of microwave, such as antenna itself. Well, that's 0.8 Kelvin. You do the subtraction, and you're still left with 3.5 Kelvin signal that you don't know what the origin is. It turns out that this was the light from the fireball universe. So just having the measurement of the brightness of the sky at one wavelength, such as 7 centimeter, wouldn't tell you that this light comes from the fireball universe. To prove this, you need to measure the brightness of the light over a wide range of wavelengths and show that the spectrum of this light follows that of the fireball. What's shown in the line, let's say green line, is the spectrum of the fireball at the temperature of 2.725 Kelvin. That's super cold, right? Like a minus 270 Celsius. That's too cold to be called fireball. This suggests that the universe in the past was fireball. And we are simply seeing the same light with wavelengths stretched by the expansion of space. So this tells you that magenta line is 4 Kelvin, yellow line is 2 Kelvin, so temperature is neither 2 Kelvin nor 4, it's actually 2.725. How was this discovery done? Let's watch the movie again.
In 1989, the Cosmic Background Radiation Probe, COBE, was launched into space. Observations from outer space without disturbance by the atmosphere brought about a remarkable discovery. The spectrum of the cosmic background radiation matched the theoretical expectation of the Planck distribution. But the best was yet to come. The shape of this curve depends on the temperature of matter that emitted light. Using this property, the temperature of the cosmic background radiation was found to be minus 270.4 degrees Celsius. However, in detail, these curves vary slightly from place to place. That is, the temperature of the cosmic background radiation has fluctuations.
That's right. So there you go. This is the globe showing you the distribution of temperatures of cosmic micro background in the sky. So COBE made the discovery of the fluctuation, and with this second generation satellite, WMAP, that we launched in 2001, we made more precise measurement, improving the angular resolution of the measurement by 35 times. So COBE had the map, which has 6,000 pixels. With WMAP, we have a couple million pixels. So we have a vivid picture of the early universe. And this is a science team of WMAP, about 20 or so people. This picture was taken in 2002. Seems like a long ago. And so let's put this into the context. We are living inside the Milky Way, beautiful Milky Way that you see in the night sky. And sky is 360 degrees. So somehow we need to be clever about projecting it onto the screen. Let's do that. We call this galactic projection. Now you're seeing the sky in visible wavelengths. Now we go to longer wavelength. First, near infrared, far infrared, and some millimeter. By the time you go to microwave, you see, of course, yourself being surrounded by the light from the fireball universe. But when you improve the contrast of the image by factor of 100,000 times, got lots of contrast, you start seeing these ripples, okay? So these are the ripples, these are the clumps of matter that existed during the fireball universe. A remarkable thing is that this is our origin. These tiny fluctuations in the early universe, they gravitationally attract each other, they grow bigger and bigger, and they form galaxies. Galaxies have stars. Stars are planets, and planets host life. Yeah, so, and that's what we are observing. Yeah, that's a direct photograph of the early universe that we took using data from COBE and the data from WMAP. Isn't that remarkable? Yeah, observations of the cosmic micro background told us a remarkable story. Okay, let's dig in there a little bit more because that seems very remarkable. So how does light of the cosmic micro background come to us? People have this impression that the Big Bang started from one point, but that's actually not true, because if that were the case, you have a light here, they are just gone by now, okay? What happens was that the entire space was lit up like this, and if you had the light source 1 light year away, or they come, and 1 year later they pass. So we are witnessing the light that was emitted far away, far away, 13.8 billion years ago. And they finally came to us after traveling space for 13.8 billion years. And if we wait more, we see light coming from farther away. But there's a limit because, okay, then can we use this to see the beginning of the universe? That's not quite possible because, as you saw already at the beginning, universe in the fireball state was opaque. You can't see beyond this wall of the so-called last scattering surface, at which light of the fireball universe was scattered by electrons for one last time. To go beyond and learn about really the beginning of the universe, we would have to use laws of physics, the power of the laws of physics, and go beyond the wall, like this.
The cosmic background radiation is the wall at the edge of the visible universe. We cannot see directly the further past beyond this wall. But these temperature fluctuations may tell us what happened in the further past.
The conditions beyond the wall of the cosmic background radiation could be thought of as a liquid with high temperature and high density. You could say it was like a hot soup. Something happened behind this wall that made waves, which can be seen in the fluctuations in the cosmic background radiation. There must have been a grand sound that shook the universe. We can learn a great deal about the universe if we can extract this cosmic sound. The origin of the sound would be the moment of the birth of the universe.
So you heard that universe was like a hot soup, like this. This is the Japanese signature soup, miso soup. Miso soup is great because it's opaque, right? And then it's not so viscous, so that when you drop tohus into miso soup, it creates ripples, just like the real universe. So the thing is, when universe was so hot and dense, the matter was completely ionized and formed a plasma. This plasma behaves like a fluid, a soup. So let's imagine dropping tofu into a miso soup, and maybe we have 2 miso soups with different amounts of miso. In one hand, you drop tofu, creates ripples. Maybe ripples propagate differently depending upon how much miso you have in the soup. Or maybe you have potato instead of miso, like Germans love, Kartoffelsuppe, but in that case, you drop kartoffel into it, nothing happens because it's too viscous anyway. So maybe that's the cosmic micro background we're seeing. To prove that, how do we analyze the data? Okay, so what we do is to decompose this image into a set of waves. And if you're familiar with image processing, you're a photographer, you are a movie director, then you're familiar with how to analyze images, and you remove high frequency noise, you retain lower frequency signals, and so on. If you're a musician, you're also familiar with not the image processing, but the processing of the acoustics data. Same thing, you decompose sounds into a set of waves and you try to play with it. Universe is the same. Here we are trying to decompose ripples in the cosmic micro background temperature into a set of waves, and we plot the amplitude of waves as a function of the wavelength. Then you see that vertical axis is the amplitude of waves, the horizontal axis is 1 over wavelengths. As you go to the right, you're seeing shorter wavelengths. As you go to the left, you're seeing longer wavelengths. And the thing is, this looks like a wave. You see oscillations. Wow, universe was like a miso soup. This is the real data sets. You see, I'm not bullshitting. This is the real thing. And the fact that the universe behaved like a miso soup, I don't know if Professor Peebles was thinking of miso soup at that time, probably not, but he was thinking of some other soup. This prediction was made in 1970. Discovery of the sound waves was done in 1999 to 2000. So sometimes theoretical physicists predict something remarkable and it takes 30 years for confirmation. Here, we really thank you who support science by paying tax. Sometimes it takes decades for exciting discovery to be made, but we ought to be sometimes patient and then enjoy hearing the exciting discoveries such as this one. I hope you share the excitement here, and we sincerely thank you for the support. So discovery was made theoretically and then confirmed in 1999. And for that, Jim Peebles shared the Nobel Prize in year 2019. Now this drawing looks pretty good actually, because that's how it looks in real life. So we took this picture in international conference in Goa, India. And then Jim Peebles holds an umbrella. I also hold an umbrella. Why? So East Asians, I'm Japanese, love umbrellas. Both men and women want to have umbrella even under the sunshine because we want to protect our skins from UV radiation. So I'm holding my wife's umbrella. Jim is holding my wife's Taiwanese friend's umbrella. So we all enjoy sunshine. Anyway. In the meantime, in the same year, 1970, scientists in Russia, Moscow, Rashid Sunyaev and Yakov Zeldovich made the same theoretical discovery that the universe would behave like a miso soup. Maybe they were thinking about borscht, I don't really know. Same year. And they thought that this thing would be so tiny that it would never be discovered. But science is such that after the decades of efforts, it will finally be discovered. Picture you see here was taken in 2003 at the Princeton. So I was a student and postdoc there. Rashid Sunyaev was visiting us. I took a picture because both Jim Peebles and Rashid Sunyaev were my hero. For anyone working in this area of research, these two gentlemen are superheroes. Now, history is very interesting. Life is very interesting. After 2012, so about 10 years after that, I came to Max-Planck Institute where Rashid Sunyaev was a director, so we became colleagues. If I told Eiichiro Komatsu in year 2003, you eventually become a colleague of Rashid Sunyaev, he will faint. Okay. So life is very interesting.
We can use a computer calculation to recreate the state of the universe this sound traveled through. The universe at this time was dense and behaved like liquid, such as a soup. Ingredients of the soup are the same as those in today's universe. Matter that makes stars and galaxies. And dark matter and dark energy exist, even though they cannot be seen directly by our eyes. Galaxies can keep their shapes thanks to dark matter providing gravity. It's thought that the universe's expansion is gradually speeding up due to some dark energy pushing space apart. These are the three main ingredients of the soup. Space expanded with time. Let's give some impact to the beginning of this model. Great. I have a pattern for the cosmic background radiation. The reason that this particular pattern does not match our observations is because the ratio of ingredients in the soup is wrong. Waves do not travel through in a thick soup like they do in a thin soup. I'll use the power spectrum to make the patterns match. I have to adjust the ingredients to make my calculation agree with the data. Incredible! The visible part of the universe, like stars and galaxies, makes only 5%. The universe is dominated by invisible components.
So this is very interesting. Our universe is dominated by invisible components such as dark matter and dark energy. Well, that by itself is an exciting avenue of the research, but today we're questioning. Let's give some impact to the beginning of this model. What impact? Who gave that impact? Who dropped the tohus into the miso soup in the first place? Because there weren't tohus at the beginning, there will be no sound waves. A leading idea proposed by Stephen Hawking and others is that nobody gave the initial kick. Tohus quantum mechanically emerged. So this leading idea suggests that we all came from the quantum fluctuations. In the very early time, the visible universe was so small that the physics that governs the small world, the quantum mechanics, has to play a role. And in the quantum world, nothing is certain. You cannot tell how much energy there is in one location versus the other. Everything was fluctuating. That's fine, but typically, this microscopic world has nothing to do with the macroscopic world, such as galaxy. So what's the missing link that connects small world to large world? And that's what we think is this idea of cosmic inflation. In the tiny fraction of a second in the early universe exponentially became large. So one thing that the coronavirus did to the society is that now we all understand what the exponential growth means. It's a remarkable rate of increase of anything. This exponential expansion is so enormous, so rapid that something of the size of atomic nucleus would become the size of a solar system in tiny fraction of a second. And that will stretch the wavelengths of the microscopic fluctuation to macroscopic scale, such as the galaxy. Now you hear that, and your first reaction is, what? How can we believe such a statement? And of course, we always have to verify such a statement by observational data. And I tell you that since the first discovery of the temperature fluctuation by Kobe in 1992, we have accumulated the enormous amount of evidence in support of this prediction of the cosmic inflation and quantum mechanical origin of all structures. So we have a pretty good evidence, but we want more evidence. And that evidence would be the primordial gravitational waves. Now, why do we need more evidence? Because Carl Sagan says the extraordinary claim requires extraordinary evidence. And we think we're talking about extraordinary claim because we are saying essentially we all came from the quantum mechanical fluctuation. We got to have a very good evidence for that. So gravitational waves stretch space in this manner. You can't see gravitational waves by eye, so let's visualize that by having ring of particles and watch how they move. So gravitational wave changes distances between 2 points in such a way that the ring of particles will distort in this form. Now, if you have cosmic micro background with uniform temperature and have gravitational waves pass through it, gravitational wave stretches space. When it's stretched, light of the wavelengths of the light would also be stretched. When wavelength is stretched, it's cold. So when you have electron in the middle of this electron will see, for example, from the left and right, cold photons, bottom and top, you see hot photons. When electrons scatter this photon and light comes toward us, okay? So light comes out of the screen and comes toward you, it's polarized. So there's a preferential direction in which electric field of the light wave would oscillate. How do we know that? Because when you have the sunlight being scattered by the windshield, this light is horizontally polarized. And to prove that, all you need is the polarized sunglasses, which will block light that oscillates in horizontal direction, but transmits the light that's vertically oscillating, and you can see through the car. Okay, so to get the polarization, you need to have anisotropic incident light, such as that created by gravitational waves, and scattering by something, in this case, electron. Okay, so if you look at beautiful temperature map taken by European Space Agency's Planck satellite, that's a third generation CMB satellite after WMAP. That's a beautiful temperature map, but then they also measured polarization. So that's the direction of the polarization as well as the intensity of polarization. Unfortunately, this is not yet gravitational wave. This is in fact polarization coming from the sound waves. And to measure this polarization from gravitational waves, we need to have more measurements. So there are multiple ground-based experiments taking data in Chile and South Pole. Now, we think that this is so important to do that experimentalists are now joining forces together to have, let's say, Simon's array. That's the joint experiment of groups in Chile and South Pole Observatory. That's the joint endeavor of the people working in the South Pole. But then we also think that it's so important that maybe we should put everything together, and this will be cosmic micro background research stage 4. If that's not enough, we're going to launch 4th generation cosmic microwave background satellite. And COBE was NASA, WMAP was NASA, Planck was ESA. This is the first time that the Japanese Space Agency, JAXA, will send cosmic micro background satellites into space. Let's see. So to summarize, toward finding our origins, the quest so far is we think we have a very good evidence that we all came from the quantum fluctuation in the early universe, generated during the period of cosmic inflation. But to have the definitive evidence for such a grand claim, we would have to find gravitational wave that was generated during inflation. So let's say over the next 15 years or so, we might be able to tell that we all came from the quantum fluctuation. Math science history unraveling the mystery, or that might have started with the quantum fluctuation. I stop here. Thank you very much.
Thank you, Eiichiro, for your excellent lecture and the fantastic movies. I'm sure it will have raised many questions in the minds of our audience. Just remember that you can follow the link on your screens if you would like to ask something. Eiichiro, I would like to ask one question first, since this is a lecture to celebrate the birthday of Stephen Hawking. I believe you knew him. Is that right? When did you meet the first time? When was it? When did you meet the first time?
So as you said at the beginning, I spent 9 years in Texas before moving to Munich. And I first met Stephen in April 2008 in a very interesting place called Cook's Branch Conservancy, which is a huge 23 square kilometer nature reserve near Houston, Texas. And this place is owned by Mr. George Mitchell, who had a close connection with Stephen. Mr. Mitchell was a very successful business person, as well as an enthusiastic supporter of physics. He's actually perhaps best known as a pioneer of shale gas technology. And Cynthia and George Mitchell Foundation donated a very significant amount of funding to Texas A&M University to found the Mitchell Institute for Fundamental Physics and Astronomy. Now, the connection is, at that time, Mr. Mitchell asked for one condition to found this institute, to connect the institute with Stephen Hawking. So the connection was established, and then physicists, not only in Texas A&M, but at the other institutions, could have opportunities to meet with Stephen in this incredible nature reserve. And I think he visited there every year. And until 2013, when he became ill, but then I met Stephen 3 times there in 2008, 2010, and 2012. And I think it was in 2010 meeting that, for whatever reasons, I don't recall anymore, I ended up playing Beethoven's Moonlight Sonata in front of Stephen after the dinner. I don't know why, but anyway, I got this embarrassing moment. Don't ask me what happened after I'm done playing. It was the first time that my wife also met with Stephen in 2010, and he gave her very charming wink. You know, it's very, all this was so memorable. And the last time I could greet with him was his 75th birthday conference in Cambridge. That was in 2017, and that was the last time.
Okay, thank you, Eiichiro, for that nice words. So I think we'll turn now to the questions from the audience. So there's Priyansh, age 14, and she asks, if there was nothing before the Big Bang, then how was there space and time for the Big Bang to take place?
Yeah, that's an excellent question. And of course, that's an appropriate question for this occasion, because that's what Stephen and his collaborators worked a lot on. Now, for more kind of ordinary researcher like me, that question is too big because we do not yet know how to make observation contact. So we don't know that there was nothing before the Big Bang. We just don't know. If we define the epoch of the Big Bang as the moment that the universe became hot, fireball, then we think that before the Big Bang, the moment the universe became hot, as you heard from my lecture, we think that there was a period of cosmic inflation. So it's definitely not nothing. Now, what happened before inflation? No one knows. Probably Stephen has some ideas. I'm sure Roger also has lots of ideas. But observationally, we're not there yet. We are still trying to figure out whether cosmic inflation actually took place. So we're still trying to, catch up with what the brilliant theorists such as Stephen and Roger were telling us. And we're getting there.
Okay, thank you. There's another question that asks, what areas of physics do you see developing most in the next 50 years? Yeah,
that's great. Usually senior researchers, I'm getting senior now, think that everything has been done. Lord Kelvin famously said, for example, no new physics will be discovered. And of course, he didn't know about quantum mechanics, right? So let's speculate, right? 50 years, I will be 96 in 50 years. I may be still doing physics, right? So let's say. So my guess is that it's going to be about life, I think. And life sounds like a biological thing, but the physics should play a big role there, right? So what's the connection? Can we make sense of emergence of life, even consciousness, in terms of physics? And also, does quantum mechanics play any role there? Because, for example, if you take what I said today at face value, everything was set when quantum fluctuations became big by inflation. Everything was set there. And the universe knew already where and when to form Milky Way and sun, solar system, Earth, and life. And if there's nothing quantum there, the fact that I'm giving you lecture this moment has been already decided to the beginning. And can we believe that? And I don't think we're ready to answer that. And then, 50 years from now, maybe we are really talking about how inflation happened, what was before the Big Bang, all the way through the emergence of life and consciousness. So I would think that that will probably be one of the big themes in 50 years.
Thank you. We have one more question that asks, could it theoretically be that the Big Bang was actually a gigantic black hole which collapsed?
Yeah, great question. And why don't I defer that question to Roger? Because I know that that's precisely what he's working on now. And he might be actually giving a talk on this during his lecture. So let's wait for that. If he doesn't answer that question, because it's a pre-recorded lecture, right? He wouldn't know that you're asking this question. Why don't you ask that question to Roger after his lecture? I'm looking forward to his answer as well, personally. Thanks for the question.
So Edgar, aged 12, wants to know, do you think the theory of general relativity will break down at the smallest length scale possible, otherwise known as the Planck length?
I think so. I think many people think that way. And Stephen Hawking, Roger Penrose, they're both working a lot on this area. And I believe both of them think that the general relativity would break down. General relativity, as we know, right? So general relativity is a classical theory that's not yet combined with quantum mechanics. And but the current best guess for what the quantum gravity idea is, which is string theory, in the Planck scale, definitely theory will be very different from general relativity. So at least we have a candidate theory at the Planck length, and we know that it's very different from general relativity. We don't know if that's true yet, but we have some idea.
We have very short time to ask one last question, and this is, what does the daily work of an astrophysicist of such high level look like?
Yeah, I don't know if it's a high level, but we check emails right? And go to the institute, and then open up the laptop, look at the data, right? Stare at it. We use some mathematical tools to analyze this data. Be hungry, get lunch, a cup of coffee, but most importantly, talk with my colleagues, students, researchers, talking. The reason why we ever go to our research institute is to talk to people. So I guess it's very much the same as your daily school life. You wake up, get breakfast, go to school, talk to people, learn from people, play with people. That's what we do. We enjoy our research, and we just go to the institute to play with the universe. That's what we do every day.
Thank you, Eiichiro. I think that's very true, the picture that you described. I'm afraid that this is also the last question, and then we have to end now the live questions. So thank you again, Eiichiro, for your fascinating insights. And I hope that everybody enjoyed the talk as much as I did. It was really great. And now I'm very curious about the rest of the lectures. And I'm now going to hand back to Anne Davies, please.
Thank you, Stella. Thank you, Eiichiro, for such an excellent lecture. We're now going to turn to our next speaker, Professor Sir Roger Penrose. But I do want to point out that if you didn't get the opportunity to ask some of your questions, then at the end of the programme, we'll have a panel of young experts available who'll continue to stay online to answer any questions live on air. I'd briefly like to introduce Hayley Macpherson, who's going to be coordinating this and explain a little bit more about it. Hi, Hayley. Can you tell us a little bit more about what's happening after the lectures, please?
Hi, Anne. Yeah, of course. Thanks. So we've put together an expert panel of young researchers from Cambridge and Munich to answer any questions that Eiichiro and Roger did not have time to deal with. So we have 10 panel members ready to answer your questions, anywhere from black holes to the Big Bang. So we have 5 researchers from Cambridge who appeared in the recent Discovery series, Universe Unraveled, who are experts on black holes and on gravitational waves. And we also have 5 Munich researchers who are experts on cosmology, galaxies, and on the Big Bang. And we're all really looking forward to your questions and hopefully a really nice discussion. Back to you, Anne.
Thank you, Hayley. That's great. And just another reminder that if you have questions, type them in to the Slido website, which is on the screen now, and you can also vote for questions. That is to say, www.sli.do and search for COSMOQ. I'm very pleased now that one of my Cambridge colleagues, Professor Harvey Rial, who's himself is an expert on black holes and Stephen's former student, has agreed to introduce Stephen's lifelong collaborator and friend, Sir Roger Penrose. Thank you very much, Harvey.
Thank you, Anne. It's a great pleasure for me to introduce Professor Sir Roger Penrose. Roger is a mathematician and theoretical physicist. His work has led to profound insights into the nature of space, time, and gravitation. In the 1960s, he developed powerful new mathematical techniques for studying general relativity, Einstein's theory of gravity. These enabled him to prove his famous singularity theorem, which provides very strong evidence that black holes are not simply mathematical curiosities, but are actually formed in nature. Along with Roger's later cosmic censorship conjectures, the singularity theorem provides the theoretical foundation for our current understanding of black hole formation. For this remarkable work, Roger was awarded the 2020 Nobel Prize in Physics. Roger has made many other important contributions to our understanding of black holes. He introduced the notion of conformal compactification of space-time, which provides the framework for a rigorous mathematical definition of a black hole. He introduced Penrose diagrams as a way of visualizing the structure of black holes. He also discovered the Penrose process for extracting energy from rotating black holes. Later in the 1960s, Roger joined forces with Stephen Hawking to extend these new mathematical techniques to cosmology. The resulting Hawking-Penrose singularity theorem provides strong evidence that our universe must have begun with a Big Bang singularity. Roger is the inventor of twistor theory, which is an ambitious program originally aimed at developing a quantum theory of gravity. Although this goal has not yet been achieved, twistor theory has found many other important applications in both mathematics and in theoretical physics. For example, in recent years, it has provided a powerful tool for performing calculations in particle physics. Roger has made influential and provocative contributions to quantum theory. He suggested that gravitation is responsible for wave function collapse, which may provide a way of avoiding seemingly paradoxical situations, such as Schrödinger's cat, involving a quantum superposition of macroscopic objects. In his 1989 book, The Emperor's New Mind, Roger argued that wave function collapse may play an important role in explaining human consciousness. Another of Roger's well-known discoveries is the Penrose tiling, which provides a way of tiling your bathroom using tiles of just a few different shapes in such a way that the pattern never repeats itself. Together with his father, Roger investigated so-called impossible objects, which are objects that can be drawn on a piece of paper but cannot exist in the real world. This had a strong influence on the artist M.C. Escher. For example, Escher's famous picture, Ascending and Descending, shows what is sometimes referred to as a Penrose staircase. Let me summarize and end with a brief description of Roger's career history. So he received his PhD from Cambridge in 1958 and held positions at various universities before settling down in Oxford, where he is now Emeritus Rouse Ball Professor of Mathematics. He has received many prizes and distinctions, too many for me to list them all, so I'll mention just a few highlights. He was elected a Fellow of the Royal Society in 1972 and later received the Society's Royal Medal and then the Copley Medal. He was knighted by the Queen in 1994 and appointed to the Order of Merit in 2000. He has received honorary doctorates from many universities, and in fact, he was due to receive one here in Cambridge last summer, but unfortunately that was delayed by the pandemic. So we look forward to welcoming Roger here in person to receive that degree sometime in the near future. Roger was awarded the Wolf Prize in Physics jointly with Stephen Hawking in 1988. And as I mentioned at the start, Roger was awarded the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. Now, to avoid any problems with live streaming, Roger has agreed to pre-record his lecture. The present lockdown means that he had to record himself from home, patiently facing a number of technical challenges. However, Roger is also here with us live and will be ready to answer questions straight afterwards. So let's now hear what Roger has to say about black holes, cosmology, and space-time singularities.
Well, thank you, Harvey. It's really a great pleasure for me to be able to give this talk in honor of Stephen Hawking's 79th birthday. And I want to talk about Hermann Minkowski's idea of space-time, which he introduced in 1908. Einstein in 1905 had introduced his idea of special relativity, but he thought of it in terms of equations and things like that, whereas Minkowski made it geometry. It's the four-dimensional geometry of space together with the extra dimension of time. So we have, imagine, say, three axes of space. These are the coordinates that you have, spatial coordinates, and then another axis to describe time. And this encapsulates the basic ideas of Einstein's special theory of relativity. Now, the important thing about Minkowski's picture is basically how light behaves. So we think of a light ray, which I have in the picture now. This is the history of a photon, if you like, a light ray, and it is tilted at so that you picture it as traveling with the speed of light. In order that it doesn't sort of point completely along the floor, you have to have your coordinates comparable with each other. So the speed of light is something that it looks like, say, tilted at 45 degrees or some reasonable angle like that. Now, of course, there are lots and lots of light rays, and they will, all the different light rays through the central point, the origin, will describe this thing called the null cone, which you see in orange here, and it's more important than the individual light rays, so let's remove that. It's more important than the axes, so remove that. This cone describes the most important structure of space-time. It tells you how light behaves. Now, if we think of Einstein's general theory of relativity, then the space-time becomes curved. At each point, we have one of these null cones, and although this looks like a two-dimensional surface, you've got to imagine that it's really four-dimensional, and these little cones, actually, the little circle at the top of them, you think of as being a sphere, but don't worry too much about that. You can get away with thinking of the picture of 4 dimensions by visualizing a lower number of dimensions. Gets a pretty good idea of the picture. Now, these light cones can behave in complicated ways. At the central point of this picture, you imagine a flash of light, and that's the light cone as it goes out into space-time, and it's tangent to the light cones wherever it goes. But it can do weird things like crossing over. You see at the back of this picture, at the top right-hand side, you will see these light rays start to cross over, and you have a thing called a caustic and a crossing region where they cross over each other. And it makes it quite complicated, but it is important to understand something about the way these cones behave on these caustic regions where they cross over. And I'll come back to that later. It will be relevant to what I want to say. Now, in 1939, there was a paper by Oppenheimer and Snyder where they described the collapse of a spherically symmetrical dust cloud. Now, dust is a technical term which means matter with no pressure. And their picture, this is now a space-time picture. I'm not sure they drew a picture like this, but this is more or less what their description was. You imagine time going upwards. So you could take sections of this picture as you go up and up and up and up, and that would be the evolution as time evolves. And the cones you will see start tilting in strange ways as they go up at the top. Now, this picture was known, as I say, when they wrote this paper, and it does describe what we currently would think of as of the collapse of a dust cloud to form a black hole. However, people, I think, didn't necessarily take it very seriously because particularly, well, first of all, you say the dust doesn't have any pressure. That's not really the important point. The important point is that everything is spherically symmetrical, so it falls absolutely radially inwards to the central point. And you'll see in the middle, you see this singularity, which is where the dust becomes infinite density because it's all focused into the middle. And people said, well, that's not very realistic because it might swirl around. It may not be completely symmetrical. It might have pressure. So why do we take this picture seriously? Well, in the 1960s, people started seeing things called quasars, well, they call them quasi-stellar objects originally. And they were very bright. They were brighter than, say, 100 or 1,000 times an ordinary galaxy's brightness, and yet they were pretty small. That's just to say, because they varied in brightness within periods of a few hours or a few weeks, which means that because of the speed of light would have to travel that distance, you would have to have something which was at least not bigger than something like the solar system. And to squeeze all that energy-producing stuff in the middle of this in single solar system means that you've got something like the kind of densities involved in the picture that you have here, the Oppenheimer-Snyder collapse. So people started to worry about whether something like this was going on, and whether, how does the energy get out? I mean, is there a radiation of some sort? And how does it get out if it just falls in radially? So people didn't take this picture terribly seriously, I think. There was, in fact, in the early 60s, a paper by Lifshitz and Kalatnikov in which they had claimed that in the general case, in general relativity, you would not get singularities. So this would imply that instead of falling into this central point, if you had irregularity, in a general case where you had not completely spherically symmetrical, but in a complicated kind of collapse, it might swirl around in a complicated way and come swishing out. So I think that was a common view that people had, that it wouldn't be, the spherically symmetrical picture was not realistic. So I began thinking about this. John Wheeler, I was working with at that time and somewhat earlier, and he was worrying about this problem, about what happens. I mean, is the Oppenheimer-Snyder picture realistic, or are the Russians right to say that when you swirl around, the thing will come swirling out again? And I didn't really know. I had a look at the paper that the Russians had written, and there was actually a serious mistake in the paper, which I didn't notice. I didn't see the mistake. What I did see was techniques which I was a little worried that they didn't seem completely convincing that these arguments would be utterly foolproof, and I wasn't really convinced one way or the other. And I remember walking in the woods and worrying about how you would characterize a collapse which had got beyond a point of no return. And well, let me go back a bit first, because I learned first about the picture I've just been showing, the Oppenheimer-Snyder collapse. I didn't see their paper, but I think I was in Cambridge in my second year as a research fellow, and I had a friend and mentor who was Dennis Sharma, who taught me a lot of physics. He was very influential in my understanding of physics. I was doing pure mathematics up to that point. And he suggested that I would go and listen to a lecture given in London by David Finkelstein. And David Finkelstein described the Schwarzschild solution. The Schwarzschild solution was the description of a spherically symmetrical body. It's the one that Oppenheimer and Snyder used, but not in the coordinates that they were using. The original Schwarzschild picture looked as though that you had a singularity at this place where the light cones start to tilt over and the light doesn't seem to be able to it gets sort of trapped at that place. It's what we now call the horizon. But people used to think of that as a singularity, because if you write down the equations in the way Schwarzschild did, you see that the metric, the description of how the light cones behave and so on, blows up. Things go to infinity and it doesn't make any sense. There were cosmologists, I think Lemaitre in particular, who had looked at this thing and decided that it didn't really, the Schwarzschild horizon, the Schwarzschild singularity, which is what people called that, this is when the radius became what's called 2m. M is the mass, and you use units where the gravitational constant is 1 and speed of light is 1, and all that's just convenient. And then this Schwarzschild radius, which would be, if you take the sun and squashed it down spherically symmetrically, then the place where it would reach this Schwarzschild radius would be a few meters. If you took the Earth, it would be, I don't know, about a centimeter or something like that. So it's very unrealistic for an ordinary star, or certainly for a planet. So people didn't really believe that these things would get that small. Nevertheless, there was work which showed if you have things like, neutron stars or white dwarf stars in particular, then you do get trouble when they possibly collapse and they cannot support themselves. So people did worry about these things. And in fact, Wheeler and others, I remember Fred Hoyle and his collaborators were really wondering whether the Schwarzschild radius might be coming in and producing some horrible thing. So if you take the Oppenheimer-Snyder collapse, you see you don't get a singular state there. It just seems to fall through until you get the singularity in the middle, but maybe that's not realistic because it would swirl around and do complicated things. Anyway, I remember walking in the woods and worrying about the thing that David Finkelstein had explained to me, and I'd worried when he explained it to me that you have this singularity apparently of the Schwarzschild radius, which is not a singularity, but using the right coordinates, you can sort of fall through it, and it's not a singularity, it's what we now call a horizon. Nevertheless, you still get the singularity in the middle, and it didn't seem that there's any way of getting rid of that singularity in the middle. And I wondered whether that was a general theorem or something. Is there a theorem which said if you had a very irregular collapse, did you still get a singularity? You seem to get rid of the one at the Schwarzschild radius, but can you get rid of it altogether? And I wondered whether there was a theorem or something of that sort. That was in 1958, and I really didn't know very much about general relativity. I started to think, what do I know about general relativity that other people might not know? And maybe that would be useful to me if I was going to try and prove something like this. And I thought, well, I know something about space-time, which is probably not very well known, which was the idea of two-component spinors. I learned about these from Paul Dirac, the great physicist, in lectures where he was describing quantum mechanics and then quantum field theory. And in the lectures in quantum field theory, I think this was the term which I went to in my first year as a research fellow, and he deviated from his normal course and described two-component spinors. Now, you see, Dirac was interested in spinors because he was very famous for having introduced the equation for the electron, which is called the Dirac equation. The Dirac equation uses what are called four spinors. They've got four components. And Dirac was, I think, aware that you could split them down into two-component spinors. But the two-component spinors were a little more primitive, but you needed two of them, if you like, two of the two-component spinors to make the proper Dirac equation for the electron. But he knew about the two-component spinors, and he described them in this lecture, which made them completely clear to me. I'd wondered about them before for various other reasons. And this picture that you see here is really a picture of a geometrical description of a two-spinor. On the left, you see the celestial sphere. So if you like, that's, well, it's either the past light cone, which goes out to infinity, that's the sky when you look out at the sky, or it's where your light rays go out into the future. It's the future sky, if you like. And so that's the celestial sphere. It is a real sphere. Now we're talking the right number of dimensions. Now, a spinor, two-component spinor, determines a single point on the sphere. So on the left, you see that point, and on the right-hand side, you see the little flag pointing out from the origin point, and the flag, where that little flag points, is the other piece of information you need to know how to describe geometrically what a two-component is. It has a curious property that if you rotate it through 360 degrees, it doesn't get back to itself. It goes back to minus itself. So you have to go twice before it gets back to itself. But that was a curious feature. And I knew about these things. I got familiar about them from Dirac's lectures. And I just thought, will these be any use in general relativity? I didn't see anybody use them before. Some people had, but not to my knowledge. And what I was rather surprised by was how it made the curvature much simpler than in the normal description. You could see that the curvature split nicely into two parts. One is called the Ricci part. That in this picture you see it causes light rays. I've got an observer at the top, and looking back, you see the light rays start to bend inwards. This is focusing due to what's called the Ricci tensor and Einstein's equations. The Ricci tensor is what the matter describes. So the matter density is described in Einstein's theory by the Ricci tensor. And the Ricci tensor focuses the light rays inwards in that way. The remaining part is what's called the Weyl tensor. And the Weyl tensor is, when you describe it in two-component spinors, it becomes a very, very simple thing. When you write it in tensors, it's a great mess. But in two-component spinors, it made a very simple thing, and I really could understand much better how it behaved. And it's important because it describes the free gravitational field. It is the analog. Maxwell has this wonderful theory of electromagnetism, where the theory has two things which compose it. There's what's called the charge-current vector, so that's the charge and the current. And then there's the field, which is the electromagnetic field. Very important because you're seeing me through radio waves and things which Maxwell had predicted. So the electromagnetic field is described by the field tensor. And then the source is the charge current vector. Now, in general relativity, you have the analog of that. The field is the Weyl curvature, and the source is the mass. The Ricci tensor is given by the mass. And you can see in this picture how very differently they behave. So the distortion is what's given by the Weyl curvature, and that is really free gravity. Now, I want to move over to the next picture here. This is a picture in the paper which seems to have got me the Nobel Prize, which is the generalization I had of the Oppenheimer-Snyder picture. You see, it really is the Oppenheimer-Snyder picture, but I've now drawn it a little bit more carefully than the one we had before. We see the dust cloud collapsing inwards at the bottom of the picture, time going up the picture, so it falls inwards towards the center. Now that is, if it's spherically symmetrical, that is the Oppenheimer-Snyder picture. Now I was interested in what happens if you wiggle this picture, that is, if you have the matter not really completely spherically symmetrical, but something irregular. Do you still get this nasty thing in the middle where the curvatures go to infinity, and it's called the singularity, and people don't like the idea of the singularity because your equations simply give up at that point. Now, is this going to persist, or when you have a general complicated collapse, does it sort of wiggle around and come swirling back out again? Well, what I thought I'd been walking around, well, it was in a later conversation I was having with somebody, with Ivor Robinson, and I had this idea of a trapped surface. Now, you see in the middle of this picture a little ring. This ring is going round the matter, it's surrounding the matter, but just a little too late because it's got inside the horizon. The horizon is described by this cylinder that you see going upwards to the top. That is where the light cones start to point inwards, and light can't escape from inside that region. Now, if you have this trapped surface, which is the little ring going, I call it a trapped surface because although, as I said before, the picture is you're losing a dimension. And that ring looks like a little circle where it's really a two-dimensional surface because you've got to have an extra dimension. But don't worry too much about that. The point about it is that you can imagine a flash of light on that ring. And as that flash of light, what's its history going to be? You can see that its outward part is falling inwards as well as the inward part. So let me move on to see what this is. Here I have an element of that. The bottom is a little, now I've drawn it as a two-dimensional surface. So we see that little element of the surface, and the flash of light, there'll be an outward flash and there'll be an inward flash. The outward flash is on the right, moving up to the right. The inward flash is on the left. And the history of that is the cone that you see. So that the little flash of light, I'm trying to draw two dimensions in the space-time at the same time, so it's a little confusing, the picture, I'm afraid, but that is the picture of what a little flash of light would do. Now here is what a trapped surface would do. Look at the top left of the picture. Here we have a little piece of surface. It's an ordinary two-dimensional surface. You imagine a flash on that two-dimensional surface all over it all at once, and if it's bending on the concave side, it will flash of light, the rays will be converging. On the convex side, they will be diverging. Now that's the normal experience. On the right top, you will see what I'm picturing a trapped surface would be like. On the one side, they're converging, and on the other side, they're converging. And that's just what you get on this trapped surface. And if you wiggle it a little bit, that will still be true. So it's a sort of what you call a stable property. You can change so that the geometry is not spherically symmetrical. It could be quite complicated, but close to being the picture that I showed you before, but not like it really could be significantly different. And you could imagine as the material falls inwards to the center, that the differences will get more and more, and the swishing around gets more and more complicated, so it could easily, you could imagine, swirl around and come out again. Now, you might think this is a very strange thing to have the light rays converging on both sides. It's not really all that strange. On the bottom of the picture, you see a general case where this can happen. I thought of 2 points in space-time, and these are their past cones, and the intersection, you've not got to imagine, if you get the dimensions right, that's really a little piece of a surface as they intersect at the bottom, and the light rays will be converging on both sides. What's strange about a trapped surface is not so much that the light rays converge on both sides, but they do this at the same time as the surface being closed in on itself. And that's what I call a trapped surface. Now, what I considered in this situation is the future of that trapped surface. So in the picture I showed you a moment ago, we had the shaded in the region to the future of that surface. What do I mean by the future of that surface? I mean that all the places you could get to without exceeding the speed of light. So that's the future of that surface. All the regions of space-time that you can reach without exceeding the speed of light. Now, what's the boundary of that region going to be like? Well, you remember on the very early picture I showed you what the light cone of a point did. It started to cross itself, and you get situations like this in this picture where you see the light rays start crossing each other, and it's really a nuisance if you want to have to think about that. But the key point of it is that you don't have to. You need to know that the light rays start to converge, and you get these things called conjugate points, that thing in the middle there. And once you find a conjugate point, you've known it's gone at least as far as where these light rays start crossing each other. And so you have to stop off before that happens. So what you get is something a little complicated in its shape as the boundary of the future of this surface, but it doesn't have all these complicated caustics and crossings. Well, I mean, you do start to cross, and when they cross, then that's the end of the boundary. So I can't go into the details of this, but it was a useful thing to think of, and it enabled me to produce this theorem, which showed that as long as the energy does not go negative, that is that when the rays start to focus, you remember I had this bundle of rays focusing inwards by the Ricci tensor, and the thing is that when you have positive energy, this can distort it, but it can't stop the inward focusing. It's got to get what we call a conjugate point to to the point which the observer is looking from. And it was this feature that you have to have a boundary. You have to have a boundary of the future which is compact. It's what's called compact. It means it's sort of finite in a sense. And this compactness is inconsistent with having a surface of evolution which is sort of non-compact. You imagine that the collapse to the black hole takes place with a very, very large region, so we can call that non-compact. It's just a very big region, and this region essentially goes out to infinity, and that collapses inwards to this thing which you can sort of focus back or project backwards to your initial surface, or your Cauchy surface, as it's sometimes called. And that Cauchy surface, you've got a finite region, which is a compact region in this non-compact space. And that's a contradiction. I don't want to go into that argument, but that was the argument which my theorem depended upon. Now, I gave a talk about this in, I think it was in 1964, at King's College London. And in the movie, you will see me giving a talk, like, it's not me, but somebody like, supposed to be me, giving a talk about this theorem. And you see in the audience, there's Stephen Hawking with sparks coming out of his head, getting inspired by this talk. In reality, he was not there. However, it wasn't so bad, because my colleague, as I mentioned, Dennis Sharma, who was very important to me in the history of my understanding of physics, he heard about my lecture in London and decided to have a repeat in Cambridge. And Stephen Hawking was at this repeat in Cambridge, and he heard the techniques I was using in the talk, and then I had a private session with him and with George Ellis, possibly Brandon Cartwright. No, George Ellis was there. And the three of us discussed the techniques that I was using, and in quite a lot of detail, and Stephen picked up on this. And initially, he very quickly used my theorem in a way I hadn't expected. You see, I was thinking of using it as a local collapse to show that the black holes produce singularities. And he thought of it in a different way. He was thinking of this describing the whole universe. So you're thinking of a universe which is non-compact, so it's not closed spatially. You must say it's going out to infinity, and you could use my theorem, but in the reverse direction in time. The arguments don't really depend on which way time is going, so you can use them one direction or the other direction in time. What was surprising to me about his use of this was to use it out to infinity rather than for a local argument. And yes, you can use the same argument to show that in a cosmological situation, if there is enough matter around to cause the light rays to converge way out. Now you're not talking about a local collapse, you're talking way out at what's called the sort of horizon that you see, and the light rays may start to bend inwards at that point. And so this was his argument. I was very impressed by how quickly he'd found this. Now, one of the troubles with this argument was that it depended upon the universe being spatially non-compact, and it might be compact. That is, it might actually close up in itself spatially. And so Stephen started thinking of generalizing these arguments in ways which did not depend on that, did not depend on the Cauchy surface. I should say a little bit more about a Cauchy surface. You see, usually in physics, what you do is you try to predict the future. So you know what's happening, say, at a particular time. And then if you have enough information on that time, you can evolve using your equations to see what happens in the future. And this surface is called a Cauchy surface. And you've got enough information so you can evolve it to tell you what's going to happen in the future. So Stephen Hawking introduced this idea of a Cauchy horizon, which is this thing with the H plus of S, which is the Cauchy horizon. And he looked at the structure of the Cauchy horizons, and it's very much like the boundary of a future, but the other way in time. And so you can use very many of the same techniques that we were using before to talk about Cauchy horizons. And this enabled him to generalize the arguments that I'd been using and to dispense with the notion of a Cauchy surface. I thought this was a really important development, and certainly when you're talking about cosmology. And so Stephen had 3 papers in the Royal Society using these techniques, And then we had another paper finally together, which we wrote, which generalized more or less all the theorems that we had before, which with a major contribution due to Stephen in this, which I think certainly one of the most important things he did. I'll come to one of the other most important things he did in a moment. But first of all, you see, he was more interested really in the Big Bang and in was that a generic phenomenon, or might have there been a bounce of some sort before, some previous universe which collapsed and somehow swirled around and came out again. And lots of people had pictures of that nature. Or was that necessarily a singularity? And that what one seemed to conclude from all this is it was necessarily a singularity. Now, I want to say a little bit more about this picture. This is a picture, basically, the standard cosmological picture that we have. You see at the top part of the picture, this exponential expansion. This is, well, various things got the Nobel Prize. This one with the observations of the distant supernova stars, of the expanding exponential expansion that you start to see at the top part of this picture. So it starts to bend outwards and expand exponentially. At the back, you may see some rather fizzly. It's not quite clear what's happening. That's deliberate because I don't want to prejudice this as to whether the universe is actually open or closed. So it might close up on itself, or it might really go on forever. I don't care in what I'm going to say here because it works either way. But it's useful to pretend that it closes up at least for a bit, because then I can draw the pictures more nicely. Now, what does current cosmology say about the Big Bang? You see, I kept worrying about the uniformity of the Big Bang. I'll say a little bit more about that in a moment. But the Big Bang is not a really very generic situation, and it's very smooth. And cosmologists like to have a look to see what's going on in the very early universe, and they introduce this idea of inflation. Inflation is described in this picture. What do you see in this very powerful microscope, or magnifying glass, which I've shown? What you see, according to current cosmology, is this inflationary phase, which looks like the exponential expansion of the remote future, but another one, which was supposed to have taken place in 10 to the minus 32 seconds, a ridiculously tiny fraction of a second. Now, that ridiculously tiny fraction of a second, I never really took it seriously. It seemed to me you had to introduce this strange inflaton field in order to make it work. And I didn't really think it did work for the reason which I'll come to, because, well, you see, this is the picture we had before, and you imagine that inflation is supposed to smooth everything out. It does other things which are more respectable. But the smoothing out of the universe, I never really thought that it worked. Why did I think that? Well, think about the time reverse of this picture. So now it's a collapsing universe, and the universe is now collapsing, and it could be full of all sorts of black holes and things which cause a great big mess. You don't expect to see this very nice singularity at the top. You see a huge mess. That's the most likely thing you would see, something much more like this picture, where you have black hole singularities all messed together and fusing a very, very general singularity. And so I thought, well, if inflation is supposed to get rid of the mess like this, why? You see here, inflation doesn't do anything. It doesn't change the picture at all. When you get curvatures this great, the inflaton field does nothing. So why did you not get a universe which started like this? Completely different from what we do see, with the Weyl curvature going completely wild, as in fact the Belinsky, when I said Lifshitz and Kalatnikov, Belinsky found I think it was Belinsky, who found a mistake in the paper. When corrected, they found a much more general type of singularity, which could really be a generic singularity, the kind of mess which I'm trying to describe in this picture here in some kind of schematic way. But nothing like the very smooth picture that we really seem to see for our universe. And I kept wondering about this. Why on earth is it not like that? Why is the universe not one of these very complicated things? And I remember thinking about all the different kinds of collapse singularities you can have, and cosmologists never thought about these. And I remember seeing James Peebles, who was the winner of the Nobel Prize last year, and he had done amazing work on the first 380,000 years of the universe existence, and we know a lot about that. And I said, why don't you consider these more complicated things? And he looked at me and said, because the universe isn't like that. And that made a big influence on me, because I thought, my gosh, it's not like that. And then I thought, why on earth isn't it like that? It's really a hugely important factor, which is very deeply connected with a thing called the second law of thermodynamics. You see, there's something very paradoxical, because when you go back to 380,000 years after the Big Bang, which is when you start to see light coming out, that's called the last scattering surface or the decoupling surface, not quite the same, but they're almost the same. And that is what the light you actually see coming from there. And it is very, very uniform. I think that's what James Peeble was really saying, is that we have this evidence that the universe is extremely uniform, way, way, way back as far as we can see it. And not just that, you see from the spectrum of the frequencies that we see that it is what's called a Planck spectrum, which means it's maximum entropy. And I thought, this is a paradox. You're going back and back and back and back in time. And according to the second law of thermodynamics, the entropy, that is the randomness, should be increasing. And you see the very earliest thing you directly see, you see randomness as a maximum. That is this Planck spectrum, which is telling you that the entropy is at a maximum. Now, in this picture here, I've got in the top three pictures the normal sort of picture people have of entropy increasing. Let's imagine a gas in a box. And we have a little smaller box, which is containing all the gas originally. In the bottom, I'm talking about the top left picture. I'm talking about the bottom right part of that top left picture. And we've got all the gas trapped in the little box. Now you open the box and let the gas spread out. So as entropy increases, the randomness increases, you see the gas spreads out more and more uniformly through the box. And that is the normal picture we see of the second law. But we see in the actual universe, way back at this 380,000 years after the Big Bang, you see the top right-hand picture, and we see the bottom left-hand picture. Now, the bottom left-hand picture is what you see for gravitating bodies. What I'm trying to illustrate here is the very extreme difference you have between a gas in a box and gravitating bodies. So imagine those as stars or something like that. And as they evolve in time, with entropy increasing, they get more and more and more clumpy. And they get black holes, right? At the end, you get black holes where the entropy absolutely rockets up hugely. Even right now in our current universe, by an absolutely enormous figure, the entropy is almost entirely in black holes, according to the famous Bekenstein-Hawking formula for the entropy in a black hole. So what we're seeing in the very early universe is this very curious imbalance between matter, top right, gravity, bottom left. So that the matter is uniformly distributed, but when I say gravity bottom left, I mean that the gravitational entropy is at a minimum. And I'm really puzzled about this. There's something very, very odd about the Big Bang. It is completely random as far as we can see, pretty well completely random as far as the matter, and completely unrandom with regard to gravity. So we have to have a theory which is imbalanced in this very strange way. Now, people try to say, well, how do you describe the singularities? Well, the singularities are where quantum gravity comes in. You see, you've got to have the quantum mechanics starts coming in when the curvatures, the radii of curvature become, well, what's called the Planck length, or the Planck time is 10 to the minus 43 seconds. I mean, ridiculously tiny scale. So you've got curvatures absolutely huge because the radius of curvature is absolutely tiny. And so then quantum mechanics would come in, and so who knows what goes on. That's the sort of picture people have. So I thought, well, whatever quantum gravity is, it must be a very, very peculiar theory. It must be very completely time asymmetrical, because it gives you, in the remote future, these black holes in this bottom right of this picture here. And in the beginning, you'll be seeing bottom left of the picture here. And why does quantum gravity give you this huge imbalance? And so for many, many years, I puzzled about this, and I couldn't make sense of it. Until I started to think about infinity a little bit more. And let me try and describe this Escher picture. It's a very beautiful way. He has these, I think there are 5 different pictures describing the infinity of what's called hyperbolic geometry. Don't worry about the geometry. What we're going to worry about is the infinity. These are, this is the first of Escher's circle limits. And you see these fish creatures. I'm going to point out particularly their eyes because they're exact circles. And as they get smaller and smaller towards the edge, their eyes remain exact circles. In fact, the angles on their wings, or whatever we call them, the fins, are the same right towards the edge. What this means is that the geometry right out to the edge is the same if we think of it as conformal geometry. Now, what is conformal geometry? See, normally you think of Euclidean geometry, you talk about distances, sides of lengths of angles. You have a triangle and you've got the lengths of the sides, and that's part of Euclidean geometry. But if we just talk about the angles, then that means you don't think about lengths. And this is conformal geometry. It's a very beautiful kind of geometry which generalizes the Euclidean notion of geometry. And here we have this thing called hyperbolic geometry, and the whole of it is depicted in this conformal picture. So the fish in the middle, as far as they're concerned, are just the same as the ones way out towards the edge, although it gets very, very crowded towards the edge, and you look as though they look to us as though they're very small. As far as they're concerned, they're just the same as the ones in the middle. Their conformal geometry is the same as the conformal geometry in the middle. So what's nice about this is with these pictures, you can describe infinity as a place. So if you are only interested in the conformal geometry and not just the sizes of things, the shapes, if you like, the shapes of small things, then you can squash the infinity down and think of it as a boundary. And that's what I want to do to space-time. So this is what I'm trying to do in the next picture. The conformal geometry in space-time is described by the light cone or the null cone. You see, if you want the metric, then you've got to put these surfaces which tell you distances. How is it distances? Well, we imagine particles zipping along, and when they heat, it's really times. It's times which define the metric. And they encounter these little bowl-shaped surfaces at the top or the hill-shaped ones at the bottom. And what determines where those things are? Well, it's the 2 most famous formulae of 20th century physics. At the top, we see Einstein's E equals mc squared. At the bottom, we see Max-Planck's E equals h nu. Put them together, that tells you that the top one tells you energy and mass are equivalent, the bottom tells you energy and frequency equivalent, that both together tells you energy and frequency equivalent. So any massive particle, I should say mass and frequency are equivalent, so any massive particle is a clock, a very, very perfect clock. And there's what this described in the picture. The surfaces are there when you have mass. What happens when you don't have mass? Well, a photon doesn't even see the surfaces, doesn't experience the passage of time at all. So as far as the photon is concerned, we don't even have the metric. You have the conformal structure. So if you have massless things, you're only interested in conformal geometry. If you're only interested in conformal geometry, then you can squash down infinity, and you can do it with a nice space-like surface. So it's like a time, if you like. It's time infinity. And that happens because of the cosmological constant, which was introduced by Einstein. We have here the introduction of a cosmological constant, which gives you the exponential expansion, but that enables you to squash down infinity to have this space-like infinity, which you can squash down to a finite boundary. What about the Big Bang? Can you stretch it out? Well, my colleague Paul Todd said this is a much nicer way of saying that the Weyl curvature, see, I was trying to say, well, quantum gravity in this funny way makes the Weyl curvature 0. Forget about quantum gravity. Maybe the Weyl curvature is 0. That's just a hypothesis. Paul Todd's way of saying it was, okay, let's say you can stretch out the Big Bang to make a nice finite boundary. That's fine. It's a very nice description that you can make both the infinity in the future and the Big Bang infinity of density in the past to make it a finite boundary. This is the crazy thing. This is my picture of conformal cyclic cosmology. The Big Bang had to be without any Weyl curvature because it was the continuation of the remote future squashed down of a previous eon. So each of these look like universes on the left. They're what I'm calling eons. The one in the middle, think of that, that's us. Our Big Bang stretched out becomes the squashed down remote future of the previous eon. Our remote future becomes the Big Bang of the next eon. Is this something, just a crazy thought that you can't experimentally think about? Well, you see there are signals that can get through. This is representing the join of one eon to the next. I'm thinking of light rays getting through. They certainly can in this picture. Can you see anything which gets through? What else could get through? Well, black hole collisions could get through. So the bottom picture, sorry, in the middle picture, I have a surface that's meant to be the crossover between two eons. In the bottom half of this middle picture, we see black holes coming together, bang, 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 running into each other, the gravitational waves coming out. The top of the picture is us looking back to the stretched out Big Bang, and we will see these little rings, which are concentric rings coming from the Big Bang, bang, bangs like this. Well, do we see them? Well, this here is a picture of the Planck data. These two satellites, one was called the Planck satellite, and the earlier one was called the WMAP satellite. This is the Planck data from the Planck satellite, and my colleague Vahe Gursajan plotted the centers of triple concentric rings of low variance. This is the prediction of the theory that you would get these. And the remarkable thing about this picture is that not only do you get this very clumpy distribution, which says something funny is going on, but you get them clumpy in the color too. Now, what does that mean? The red ones, the color coding tells you, according to the theory, that they're very, very distant, even outside what's called our particle horizon. The blue ones at the top are much closer. They're within our particle horizon, according to current cosmology, but they are super duper clusters of galaxies or something. If you're going to explain this picture, you've got to have some theory which explains why the universe is in this description. These are observations, complete just observations. You see this using a particular way of analyzing the data from the Planck data, and you see this very curious inhomogeneous distribution explained in the theory are described by there being huge lumps of concentrations of materials in different places. And what about this? Now, this is the Hawking evaporation of a supermassive black hole. That's why I said I would get around to this. This is the Stephen Hawking's really most important contribution to the whole of the subject. And here we see a black hole evaporating away. We don't just get the Oppenheimer-Snyder collapse. If you wait long enough, and it could be a huge length of time for the most massive of the known galactic clusters, who expect supermassive black holes, which would take something like 10 to the 100 years or more than that. That's 10 to the power 100. So 10 to the 100 years, something like that, for them to disappear, more than that probably. And they disappear with a pop at the end. You see all the mass of that black hole goes out in radiation. And you might say it's all lost. But in the conformal picture, it's not all lost. You see, this is a picture from a paper written by Christoph Meissner, Pavel Nurowski, and myself. Came out about 6 months ago, or a little bit more than that, I think now. The bottom horizontal line represents the crossover, according to the theory. Now, maybe there's some other theory, but the crossover is the join between the previous eon and our eon. So that little point called H, that's what I'm called a Hawking point. Why I'm calling it a Hawking point? Well, because the little line leading up to it from below it is meant to be the history of a supermassive black hole. And all the radiation of it, remember the Escher fish? When they get close to the edge, it's all concentrated in a little tiny point. So the entire radiation from that supermassive black hole comes through in that little point. It now spreads out through the 380,000 years that James Peebles was talking about to the last scattering point, or the decoupling point. It would be spread out to a radius of about 8 times the diameter of the moon. And so we would, according to this theory, expect to see spots in the sky which are something like about 30 times or maybe 50 times the average variations of temperature in the cosmic microwave background. Do we see them? Yes, we do. We see several of them. We see at least 6 of them, which are seen in exactly the same places in both the WMAP and Planck data, in exactly the same points. Apparently nobody's seen these spots before. Why? Probably because they've never looked, because they think that inflation eliminates these signals completely. But we see them, and in this paper, Christoph has this very clever way of doing the analysis, and the analysis tells us that these points are there with a 99.98% confidence level. So that's a very strong confidence level, that these spots are there. Exactly where they are, we don't have such a great confidence level, but the fact that these 6 points are seen both in exactly the same places in the WMAP and the Planck data, I think is strong reason to believe that those are actual Hawking points. I think this is an indication that a lot more study has got to be put into this. I'm not saying that these are necessarily actually Hawking points. I think they must be. I can't think of any other explanation. It's certainly not part of the inflationary picture. The inflationary picture should wipe these things out completely. I have no idea how it could be accommodated within conventional cosmology. I would be very intrigued to see an explanation for these spots in any other theory than the one I've been putting forward. So that's the story as it stands at the moment, with the singularities in black holes and the singularity at the Big Bang, and what is the nature of them and how do we understand singularities. It's a big question for the future. How does quantum mechanics combine with general relativity in the appropriate way? And I think these issues are things that we will be interested in and will confront science for many years to come. So thank you very much. It's been a great honor for me to be able to give this talk.
Okay, well, thank you, Roger, for your fascinating lecture about black holes, and apologies for the technical problems that we seem to be having at the moment in trying to get Zoom to work properly. Now, remember, it's possible to ask questions about the lecture using the Slido site. So before we go to those questions, I thought I'd start by asking some questions that occurred to me when I was listening to your lecture, Roger. So what struck me when you were describing your singularity theorem was that the way you described it was very visual. And so I was wondering, was this the way that you discovered the theorem? Did you visualize how light rays emanating from a trapped surface would have to behave before you sat down and worked out the mathematics?
Depends what you mean by mathematics. I mean, it's certainly getting a feel for what boundaries of futures look like. You see, I'd worked out a lot of that from another problem I was thinking about, which had not to do with black holes at all. I was looking at a problem about asymptotic gravitational radiation, if you like. And I had written a paper for the Royal Society, which actually came out almost at the same time as the black hole paper, because the black hole paper came out much more quickly because it's physical letters. But the other one was about how zero mass fields, including gravitation, behave in the asymptotic limit. And one of the problems I ran into there was the shape. You have this geometrical way of looking at infinity, which was very useful in order to answer questions like what happens to what happens to gravitational radiation and what is radiation. And you like to go out to infinity. And usually people do this by complicated analytical procedures. And I much preferred to do a conformal transformation, which brings infinity into a finite place. You could just look at it. And the problem was whether infinity had the right sort of shape. I won't go into the details of that. But I ran into a problem, and in order to solve this problem, it wasn't really important for the paper, but I really needed to clarify it for myself. And I put an appendix in this paper, which had to do with, roughly speaking, the shape of infinity. And the techniques I used for that were very much what I needed to use in the black hole problem. So I had these techniques more or less at hand. I didn't know quite how to use them in the black hole problem, but when I had the idea of a trapped surface, it did not take me long to realize that the boundary of the future of that trapped surface would be a compact region, and that there was some contradiction involved in mapping that back into the initial surface. So it was having that experience with my other paper which gave me the understanding I needed. Now, how much is that visual, is your question? Well, a lot of it is visual. But to what extent is it's visual and analytic at the same time? I mean, you have to know what to trust in your visual pictures and what not to trust. So it's not there's not a clear division between these things. But certainly I think about things in a very visual way. That's certainly true, yes.
Good, thank you. So a second question is that your theorem tells us that singularity formation is a robust prediction of general relativity, but to conclude that the singularities must lie inside black holes, you had to introduce your famous cosmic censorship conjecture. I was wondering if you could just say a few words in trying to describe that conjecture in general terms for our audience.
Well, you see, in fact, the Nobel Committee was rather generous to me in a way, because my contribution did not actually tell you that black holes were a robust prediction. What it did say is that singularities are a robust prediction. Now, the thing is that I suppose the natural thing to expect is that these singularities are hidden in black holes, but it's not a theorem. It's not a mathematical conclusion that one can necessarily derive. And in the paper I wrote, which has a lot more in it than the paper that apparently got the Nobel Prize, there was one that I wrote for the Italian journal, and Nuova Cimento, who was a special issue of that, was a conference. But anyway, I did raise a lot of questions, Part of it was how you get energy out of black holes and things like that, the rotation of a black hole. But the question I raised right at the end was, is there a theorem or some general principle which tells you that these singularities that you could see directly, a naked singularity, would be one from which information could come directly out of the singularity and not being shielded from vision by the horizon? So in a way, you see, it's not, the horizon is the clothes, and if it's naked, it doesn't have any clothes, you see. So it would really be cosmic censorship was the censoring that you didn't have these singularities you could directly see. Now, I was quite open-minded about that. And in fact, a paper I wrote later, I'd actually explored the possibility you might have naked singularities. And this was the one that led to the thing called the Penrose inequality, because it was a condition which showed that if you could violate this inequality, then you would have naked singularities. And I didn't prove that you couldn't violate it. That was I guess the Penrose inequality was a conjecture. I did not prove anything. It was quite curious because Stephen Hawking regarded it as a convincing argument that naked singularities didn't exist, because I had failed to prove that they did exist or something like that.
Excellent. Maybe I should ask a question coming in from our audience. So I have a question here from Sunak Chakraborty, who's in India, who asks, will an observer falling into a black hole be able to witness all future events in the universe outside the black hole?
And the answer to that is no. I mean, if I just take the standard Oppenheimer-Schneider model, which is spectrally symmetrical, then you can see if you take one of these time-like curves which end on the singularity, its past is a very definite region, and it certainly does not see the whole of the universe. It's a very explicit part of the universe you see. And I would imagine that's the general case. So you would certainly not expect to see the whole of the future of the rest of the universe. No, very far from it.
Okay. Another question by someone called Vicky from Hungary, who asks, can a black hole fully evaporate through Hawking radiation? If not, what is its long-term fate?
Well, of course, there are unknowns about this, but my expectation is, yes, it would evaporate away. You see, the question is what happens at the very last moment. And I tend to call this the pop, which happens at the end, because it's relatively small. There is this event when the last moment of the black hole's existence, and the amount of radiation, the intensity of the radiation increases as it gets smaller. It gets hotter, I should say, and it gets very, very hot and infinitely hot right at the end. But I'm not. What was the question exactly? I can't quite remember the
question was: can a black hole fully evaporate through Hawking radiation? So,
well, you said. I mean, yes, would be the answer.
Good.
Of course, there's unknowns about what happens at the very last moment. And of course, you'd expect at the very last moment your black hole has got down to maybe something like a Planck scale, which is a few grams, or 10 to the minus 5 grams, I should say. And no, it's 10 to the 5th. I've got it the wrong way around. How many grams is a Planck mass? Anyway, whatever it is, it's quite small, but not infinitely small. But nevertheless, one can start questioning what happens at that point. But almost the entire black hole has disappeared by then, so why not the whole thing? Sure, the whole thing should probably disappear completely, yes. Into radiation.
Yes.
The radiation is there.
We just mentioned Stephen Hawking, and we're celebrating Stephen Hawking's birthday today. So you were a collaborator with Stephen and a lifelong friend of his. So I just wanted to ask you about Stephen's most important contributions to physics. So in your talk, I think you mentioned Hawking radiation, and we just discussed that. And that this effect is such a big discovery that sometimes it tends to overshadow some of Stephen's other work on black holes. So I wondered if you could tell us briefly what you think.
Did.
Yeah, what do you think was Stephen's
most important thing? But a clear formula for the entropy in the black hole, it's all part of the same problem. I mean, Eckenstein had a rather slightly hand-waving argument to suggest that the area of the black hole, the area of the horizon, was a measure of its entropy. And Stephen had a much clearer argument to show with a factor of a quarter, which told you more or less, well, exactly what one would expect for the entropy of a black hole. And I think that all goes along with his the Hawking evaporation, Hawking radiation. So that's all one story, if you like. And I regard that as his most important contribution. He did do other significant things with black holes. One of them had to do with the asymptotic behavior of a black hole. And we're thinking classically now, not to do with the Hawking evaporation. But you see, a black hole might be irregular. I wouldn't expect it to be exactly like the Oppenheimer-Snyder picture. It could be with some irregularities, but they very rapidly radiate away, and you end up with, well, the sort of thing you get is the Kerr solution, so it would be rotating, and that has a sort of stability about it. Now, the question was, is the Kerr solution this limiting, or is it unique as the kind of stationary black hole that you could get at the end? And it was really Brandon Carter who started. Well, go back a little bit more than that. It was Werner Israel who, for the non-rotating case, he was looking at what static configurations could you have with black holes, and it turns out to be the Schwarzschild solution, that all the other moments will there was a period of time when people believed that somehow that shows black holes didn't exist because you could only have the spherical ones. So what happens to all the unspherical ones? But the point is that all the irregularities get radiated away. The quadrupole, everything up to the quadrupole moment, including that, disappear in radiation, and you're left with just the static Schwarzschild solution. But if it's rotating, then you can also have the Kerr solution. And Brandon Carter started this. There were several people involved, David Robinson and Stephen. You see, the thing is, the work before that was to show that if you had axisymmetry, then it had to be the Kerr solution. And what Stephen showed by a rather general argument, which was an ingenious argument, more or less showed that you had to have axisymmetry in the limiting case. So that was an important contribution to this whole discussion.
I guess that there was also...
What else to do with black holes? Oh, sorry, go ahead.
So there was the area theorem, or I guess was one of the...
Well, there's a little bit of a question about that. I mean, the story there, I've never got to the root of it, and I don't quite know what Stephen thought about it. You see, there was a story there. I was visiting Cambridge, and I remember having quite a long discussion with Stephen in one of the lecture rooms. And I was describing to him this general tendency for the area to increase, and that this was a general result. And he didn't seem to know that at the time. I can't remember whether my paper with Floyd was out by then or not, but certainly we'd done this work. And then I was staying in Cambridge, and the next morning I got a phone call from Stephen, and he said that this result we were talking about the previous night, he had an interesting idea about it. And he said, oh yes, what was that? Suppose you have two black holes, and they collide, and you can get, from using the area, the fact that the area cannot decrease, is you get a limit on how much radiation comes out, something like that. And I remember that was a remarkable idea. And I said I'd never thought of doing it that way. And how that you could think of the area of the black hole as being a composite of two different black holes together. So that was what he did. Now, his later memory of what happened was somehow that his memory was different from mine, you see, because I did talk about this theorem to him already the night before. But then he had this inspiration when he was waking up in the morning or something, I can't remember what it was. And that I took to be the fact that you could apply this result to a pair of black holes. And you could get a limit on how much radiation could come from a pair of black holes. But then it became this area theorem as he was starting with as his greatest contribution, and I got very puzzled about. Sorry, let's stop this story and go on to the next question.
Of course, that limit on how much gravitational radiation you can get is quite relevant now that we're observing gravitational radiation from black hole mergers. Just another very quick.
Yes, no, that's right. It would be relevant to that. Yes.
Yeah. Yes. Another very quick question is there a maximum size limit for black holes?
No, except there's a limit to how much matter there is in local regions in the universe, I suppose. But no, there's no theoretical reason they can be as big as they like. Mm-hmm. I mean, big ones can crash into each other and make even bigger ones. Depends on how much is available. I mean, if there's no matter around, you can't do much with it. Mm-hmm. But there's no theoretical limit to the size of them.
Another very quick question, I think we've only got a minute or so left, is in your lecture, I think you mentioned Paul Dirac and spinors. I was interested because
yes.
Paul Dirac, a former Nobel Prize winner who discovered the equation governing the electron, he was at St. John's College in
Indeed.
Cambridge at the same time as you. So did you have any interactions with
yes,
Paul
indeed.
Dirac?
Oh, yeah, quite an important one, you see. More than once, but the main one was, I remember being opposite him at dinner on one occasion, and I said I had some ideas that I wanted to discuss with him, and so I had a conversation with him in the lecture room about the spinor description, how you can write the curvatures in terms of spinors, and that I pointed out this equation that you have on the viral spinor is this very symmetrical object and looks like a massless field, and the question was, was this any use for quantization? And his remark was, well, you have to have a Hamiltonian, you see. Well, that's just... No, he was very interested because he gave a recommendation for me when I went to my job. I guess I had a job in the University of Texas. And they showed me the recommendation letter I had from Dirac, and it was very short, but it was coming from Dirac. He said, it was based on this conversation where he said that I had done this interesting thing and it was all my idea that I developed. And I suppose that was a nice recommendation to get from a man like Dirac, certainly. Yes. But I've had other experiences with him too, some of them not quite so good as that one. There was an occasion when I'd written a review of his book, which is a very nice book, very compact book, and he got something not quite right, you see. It was to do with whether the energy was localizable in a gravitational wave. I said, well, actually, it isn't quite true. And he didn't normally talk to people, but I was at some reception, and I was one end of the room, and Dirac was at the other end of the room. And he saw me, and he came walking up to talk to me, and he complained about what I'd said in the recommendation. And I said, well, look, the energy isn't localized in a gravitational wave, and I explained why. And then he went away again, so I guess he must have agreed with me at that point. But he was somebody who didn't like to be wrong. So if he said something which wasn't quite true in his book, which he did in this case, and I pointed it out in the review. And so I guess he felt a little uncomfortable about that. That was only a very, very minor point, that it wasn't, what he said was not quite correct, that's all.
Everyone makes mistakes, even Nobel laureates, I guess.
Oh, yeah, even Dirac. Not often, but still. Yes.
Okay, well, this has been really interesting, but I'm afraid that's all we have time for today. So thank you very much, Roger, for answering our questions.
My pleasure.
Personally, I must say I found your description of the history to your Nobel Prize winning work in your lecture absolutely fascinating. And I've also enjoyed greatly hearing your reminiscences of working with Stephen Hawking. So thank you again, Roger, for being with us this evening and letting us know about your exciting work on black holes. So I'm now going to hand back to Anne Davis.
Thank you, Harvey. And thank you, Roger. It's been such a privilege having you with us this evening. Thank you so much. I'd like to apologise for the technical difficulty we experienced in the Q&A. It's one of the consequences of lockdown. I'm sorry.
Thank you, Roger.
For me to thank the organisers of this meeting, the Centre for Theoretical Cosmology at the University of Cambridge, our partners at LMU, and the amazing team at Intel Studios and Four Winds Creative for the incredible help with this live stream. It's been a great pleasure also to work together with the Stephen Hawking Foundation, and we hope to be organising lectures in honour of Stephen Hawking in the future as well. It just remains for me to say that if your questions were not answered, then our expert panel of young scientists will continue afterwards to address the issues that are important to you. If this live stream ends, then please follow the link that's shown on the screen now to see Hayley introduce the panel. Thank you so much for listening. Stay tuned for future Hawking lectures. Good evening.